Okay, good morning. So the next item on the synopsis on the website says motion of a particle in a magnetic field. But I think it's better that we postpone that. We don't need to handle it now. And now open this new topic, this new chapter, which is chapter 4 in the book, the relationship between transformations and observables. We'll come back to the magnetic field later. But we have this week, and this is I'd like to make sure we do this thing properly. Now, this topic is off syllabus, right? But it is actually very important. It's at the core of quantum mechanics, and it's at the core of 20th century physics. And I think you'll find it illuminating because it should explain why the time-dependent Schrödinger equation takes the form that it does. It should explain why the momentum operator takes the form that it does, why the canonical commutation relations take the form that they do. So I think it explains many things, but for historical reasons, it's not actually on the syllabus. Okay, so we know that this thing is a function. This thing is a function of x, where x is now going to be a position vector. This is being the amplitude to find your system, your particle, whatever, at the location x, right? So it's because it's an amplitude which depends on x. It's a complex valued function of x, and so we can Taylor series expand this. Physicists always assume you can Taylor series expand everything. So we Taylor series expand this, and we say that if we evaluate this at x minus a, then that is going to be essentially, well, to keep the notation simple, we call this psi of x, right? So this is going to be psi of x minus a dot d by dx of psi plus a dot d by dx of psi squared over 2 factorial minus blah, 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 blah. This is just the Taylor series expansion in 3 variables. It's covered in some prelims course, right? And yeah. So this is just the Taylor series expansion. And we now make an observation that this can be written with our now that we understand how to take a function of an operator, and we realize that d by dx is an operator, we can write this as the exponential of minus a dot d by dx operating on psi, where we're defining this exponential to mean this thing raised to the 0th power, namely 1, plus this thing raised to the 1st power, plus this thing raised to the 2nd power on 2 factorial, and so on and so on and so forth. That's what we mean by the exponential of this operator, okay? But we notice that this can also be written as x. This is working on psi of x. This can be written by the rules of operators and the definition of p as the exponential of minus I p upon h bar dot p over h bar operating on the ket of psi. Let me just remind you what my authority for that is. My authority for that is the observation that, or the definition of p, which was that x p psi was by definition minus I h bar d by d x of x psi, and this animal here could be rewritten as x psi. Okay, so I can just make a change of notation here because of this. And where I've replaced p now by the function of p that you see there. And then we have a function of this operator. So what have we discovered? What we've discovered is that x minus a, this is the bottom line on this little piece of calculation, which is really only Taylor series expanding into psi, is equal to x on u of a of psi, where u of a is a new notation for, it simply means the exponential minus I a dot p over h bar. So that's what u of a means. This could also be written as x minus a on a psi is equal to x on a psi primed, where a psi primed, the ket, is by definition u, the operator, operating on a psi. Right? We've just called this thing psi primed. So let's think about, so that's just mathematics, and it's nothing but Taylor series expanding and a little bit of slight sophistication in taking functions of operators, but we've begun to do that. We understand that that comes with the territory. What does this physically say? It says that so there is, if you use this operator on a psi, you get a new state, a psi primed. What's the point about this new state? Well, if your system is in this state, the new state, then the amplitude to be at x is the same as it was when we were in our old state, somewhere behind our current location, back at x minus a. So here's a visualizer. Here's meant to be a picture of this. If we can get it to come back. Yes, we can get it to come back. And if I could find a pointer, which I probably can't, never mind. But so if a psi were that sort of, if the probability density associated with a psi were that spherical blob on the left, the lower left, and A is that vector displacement up there, then the amplitude to be at some point, take any point x in the sphere of a psi primed, if you move back by A, you come to the corresponding point on the spherical density associated with psi, and the amplitude in a psi matches the amplitude in a psi primed. That's a sort of visualization. This statement of what this is telling us, it's telling us that at psi primed, the amplitude to be at psi primed is the same as the amplitude over here at a point back, which means that psi primed is the state that our system would be in if we were able to just shove it down the vector A, to translate it by A. Then we will get a new state with these properties. So what have we done? We have discovered what the operator u of A does. U of A shoves the system by a displacement A. Now, A is just an ordinary boring vector. This is an operator, but this is an ordinary boring vector. It's a set of three real numbers, and we can differentiate. We can do d of psi primed. So the state that you get is a function of A, right? So we can do d by d psi primed of A sub I, well, A sub j, shall we say, right? To avoid confusion between the index I and the square root of -1. So we consider the rate at which this thing changes when we change the parameters that appear in here. When we differentiate this exponential, as everybody knows, when you differentiate an exponential, you get the exponential back. That's just by the magic of that particular power series that defines the exponential. And then we need the differential, so that's going to be u. So differentiating u, we're going to get back u. But we're also going to get the derivative of this with respect to A sub j, which is going to be minus minus pj over h bar. And then, of course, psi will stick around because psi is not a function of A. So if we would now set, and now we can just recall that this thing is psi primed. So I now have that d psi primed by dA sub j is equal to minus I, let's multiply through by IH bar. And then we have that this is equal to pj of psi primed. Whoops. So this now answers a question which I forgot to ask at the beginning of the lecture, which is, what actually does the operator P do? An operator associated with an observable. So with each observables, we have associated an operator. We did it originally by saying that Q, the observable associated with Q, was by definition Qj, Qj, Qj. And this operator, we're taking advantage of the fact that a Hermitian operator is uniquely characterized by its eigenkets and eigenvalues. So if you specify these, you specify these. If you specify this, you specify this. There's a relationship here, which we found useful. We've discovered that the expectation value of Q, for example, is equal to this mathematical animal and other things, and other useful things. We found the rate of change of expectation values depends on the commutator of Q with the Hamiltonian operator, which is the operator associated with the energy, et cetera, et cetera. But we haven't actually addressed or answered the question of what these operators that we're introducing actually do to states, because an operator turns a state into a new state. So, for example, so the operator Q turns psi, if we expand psi in its eigenstates, right? So if we write it like this, so we know we can expand any psi thus in the eigenstates of this operator, and then we know how to use this on this. So this is equal to the sum Qj, oops. So when we use the operator Q on psi, we get this stuff here, which is some long gobbledygook. But if we measure Q, then psi goes to Qk for some k. It doesn't go to this long list of stuff. It goes to one of these things, and the one of these things is chosen at random, somehow by nature, not discussed by theory, no answer offered by theory, merely probability distribution under which we get one of these things is predicted. But we know that the state of psi on making a measurement collapses into one of these states here. So the operator Q is not doing measuring. That's the point. And we have discovered, apropos of the operator P, what is it doing? What P does is give you the rate of change of your state when you shove something along. So Px gives you the rate of change, Px of psi gives you the rate of change of your state if you shove it down the x-axis. So we're learning what the operator Px does, and what it does is not measure, but displace. Let's for a piece of practice, let's check this out on. Let's check this out on this state. Let's, for fun, apply UA to this state, which is the state of definitely being at x, and make sure that we can produce x plus a, the state of being at x plus a. Because if it's true, if you take the state x and you displace it by a, you must have this state, right? Let's make sure that this is the case. So what we want to do is use UA on x. Now this operator here is a function of the momentum operators, right? It's that exponential a dot p. So the natty way to do this is to decompose this into a linear combination of states of well-defined p. So we write this as d cubed p of p x p. So basically, I've subbed an identity operator in front of the x. This is a boring complex number. What is it? It's the complex conjugate of the wave function associated with having well-defined momentum. So we know what it is. It's e to the minus I p upon h bar dot x over h bar to the 3/2 power. We discussed that when we talked about generalization to 3 dimensions. That's what this complex number is. This operator ignores that complex number because it's a linear operator and goes straight to its target, which is this. Then all the p operators in here meet their eigenstate, p, and get transformed simply into their eigenvalues. So this becomes, when this thing hits this, the p's in here are operators, but when they meet that, because that's its eigenstate, they simply become eigenvalues. So we get an e to the minus I a dot p over h bar times the ket, the eigenket left behind, and still we have to do a d cubed p integration. Right, so this is no longer an operator because it already worked on that and produced its eigenvalue. So we can rearrange this. We can put those two exponentials, whose arguments are mere complex numbers, we can gather them together, and this becomes the integral d cubed p of over h bar. Sorry, that isn't barred. That's unbarred. Excuse me. 3/2 power. H, Planck's naked constant. E to the minus I p, well, let's write it. It doesn't matter what order we write these in, you see, because this is a number and that's a number. So I'm going to write this as a plus x dot p upon h bar up. But if I now ask myself, what is x in this notation? I probably should have written this down originally. It was d cubed p over h 3/2 power e to the minus I x dot p over h bar p. This is just a standard expression which I've essentially used above for decomposing a state of well-defined position as the superposition of states of well-defined momentum, where this is this thing here is nothing but px. So since this is the general formula, this state that we're producing, ua on x, is given by the same formula, but with x replaced by x plus a. Right? Because the only difference between this formula and this formula is that here we have an x, and therefore we have an x, and here we have an x plus a, so we should have an x plus a. So this establishes, indeed, that x plus a is equal to u of a on x. So that's just a particular, very vivid example of a basic principle. So what we want to do now is generalize this to any continuous transformation. We always require proper normalization. We require psi is equal to 1. Why? Because this tells us that the total probability to get some measurement, to find something, is 1, right? That's why we're completely wedded to that normalization. So we're interested in transformations that preserve this property. This shoving it along transformation was one example. In a minute, we'll talk about the transformations associated with rotating our system around some axis. But there are many transformations we might make. So what we're going to say is that psi goes to some newfangled state, which is some operator u on our old state. And in light of this, we're going to restrict ourselves to 1 is equal to psi primed. If we take our new states, they've got to be properly normalized, which means that we're looking at psi u dagger u psi. All right? So we require this is 1, but this is by definition u psi. So if we take the mod square of this, we're looking at that, where u is this as yet undetermined operator. And the thing is, so this has to be true for all psi. For any quantum state, this has to be true, that this thing is 1. And there's a technical detail about establishing that this is 1. There's a box in chapter 4 of the book doing this, which I don't propose to go through. It's very straightforward and simple, but I don't want to take the time to do it because it's mere mathematics. From the fact that this has to be 1 for any psi, we can deduce that u dagger u is in fact the identity operator. Okay? From this statement, this follows fairly straightforwardly, but I'm not actually proving it right now. So operators of this sort, as I expect you know from Professor Esler's course, are called unitary. So unitary operators are precisely those operators which leave the length of our states unchanged. And in the present case, for physical reasons, the length is 1. Now we're dealing with one such earlier on. Let's suppose that u is a function of theta. In that case, u is a function of a. Let's theta just be some parameter so theta is a parameter which we can make small. Well, shall we say, which can go to 0. So the idea is that theta is the amount by which you've transformed. There, a was the distance which we had displaced. So a is analogous to theta. Here, theta just stands vaguely for the amount by which you can do something. And we want to be able to say that we can reduce this amount continuously down to nothing when we're doing absolutely nothing. So we're going to have that u of naught is the identity operator because that's the operator that does nothing. So we want to have this parameter. And now we're going to argue that if theta is small, we should be able to Taylor expand. I said physicists assume you can Taylor expand everything. So we're jolly well going to Taylor expand this. So we're going to have that u of theta, which is now small, is u for theta equals 0, which we've said is 1, the identity. And now we're going to write the first order term in a slightly funny way. We're going to write minus I theta tau, and then we'll have terms order theta squared. So this is a Taylor series expansion, only the first two terms, the 0 term and the first derivative term, and all the other terms we just got wrapped up under order theta squared. Not saying what they are. And this is an operator. It has to be an operator because this is an operator. This, of course, is an operator. That is a mere number. That is a mere number, a real number. So therefore, this has to be doing the operating. But we've just chosen a particular way of writing the first order, the first derivative term in a Taylor series. So this is a Taylor series. And relies only on the idea that theta, there's a whole family of transformations which could be reduced to the identity transformation as theta goes down to nothing when you don't do anything. Okay, now we want to look at this condition. We want to have a look at the condition that the identity is u dagger u. So let's write u. What's u dagger if this is u? U dagger is going to be I dagger, which is I. And then we'll need the dagger of this, which is going to be plus I theta tau dagger plus order theta squared, which we're going to ignore. And that has to be multiplied on I minus I theta tau plus order theta squared, which we're going to ignore. So when you when you multiply these two brackets together, ginormous job in principle because there are all this infinite number of terms and this and that, but we won't need to bother with much algebra. We must get the identity operator, and we must get the identity operator completely regardless of what theta is, right? Because this is meant to be, this is a unitary transformation regardless of theta. So let's work this out. This is equal to the, so what do we have? We have the lowest order term is this on this. Then there are first order terms, which you get this on this and this on this. So we're going to have plus I theta tau dagger minus tau. And then we will have terms like this on this, which will be order theta squared. This on this will be order theta squared. We'll have this on this, which will be order theta squared. So plus order theta squared. We've accounted for everything through linear order. So this is supposed to be true for all theta. Doesn't matter what theta we take. Should be true. If it's going to be true for all theta, then we can equate powers of theta on both sides. So the coefficient of theta to the naught, namely the identity, should be the same on both sides. Well, it is. That's a relief. The coefficient of theta to the first power should be the same on both sides. On this side of the equation, there is, well, the coefficient of theta to the first power is nothing. So it had better be nothing on this side too. So this implies that tau dagger is equal to tau. That is to say, tau is Hermitian. Hermitian operators, we suspect, are associated with observables. So the argument here is that every such transformation is going to be associated with a Hermitian operator. And the reason this I was put in here, this was totally gratuitous, right up there. The reason that I was put in there, which was a totally gratuitous decoration, but it went in because that ensures, looking forward, it ensures that tau is a Hermitian operator rather than an anti-Hermitian operator, which it would have been if the I had not been put in. So there's a suspicion that this tau, and it will always turn out to be the case, that this tau will be associated with an observable. This is how observables become associated with operators in both classical mechanics and quantum mechanics, or should have said in quantum mechanics and in classical mechanics. It turns out that it's true in any mechanics. Right, and if we write the equation of psi primed is equal to u of theta times psi is equal to 1 minus I theta tau plus psi. And we do d theta primed, d psi primed by d theta, we find that this is equal to minus I tau psi plus order delta squared. So if we put theta equal to naught, then the delta squared goes away. The order theta squared. And multiply this equation through by I, and we get a very important equation, which is that I d psi primed by d theta is equal to tau. So this the operator, tau, the Hermitian operator tau, which we suspect is connected to some observable, well, will turn out to be connected to some observable in every case, is the thing. What does it do? What it does is it measures the rate of change of your states when you change the parameter theta. So this is a generalization of, where are we? This equation here, yeah. All right, so this is a concrete example of this. Now this equation has a tiresome h-bar here. Why has it got a tiresome h-bar here? Because in that exponential, there's a tiresome h-bar on the bottom. Right? So here we had the exponential of minus I a dot p over h bar. And if you do the Taylor series expansion of that, you get 1 minus I a p over h bar, so that the role of tau in our conceptual apparatus here is played by p over h bar there. And it's an unfortunate historical accident that momentum, that this operator, which we call the momentum operator, has been defined with a wretched h-bar, so we have to divide through by h-bar to get rid of what we shouldn't have put in the first place. So it's one of these many cases in physics where history forces us into a bad notation, and even a degree of intellectual muddle, that h-bar had better not, would have been better left out. But the reason is that momentum came to Isaac Newton's attention before quantum mechanics or this stuff was thought about, and so it came to mean something which is really a derivative thing, which is really something which follows on from momentum's fundamental role, which is something which shoves your system, which spatially translates your system. Okay. And if we want to do so we've defined tau. Tau came in here through a formula for u of theta when theta is small. We would like to know how to do u of theta even when theta is large. So for large theta, well, what we should say is take a transformation through large theta in n steps. So if we are told to find out what u is for a large value of theta, the way to go is to make many transformations, one after another, through small steps of length theta over n. Then, if n is big enough, no matter what the value of theta we're given, we can write that what we can do is we can say at psi primed, which is u of theta at psi, of course, is equal to u of theta over n, u of theta over n, u of theta over n, n of these terms all multiplied together operating on a psi. So we make a transformation by an amount theta over n, and then another one theta over n, so there are n terms. And each one of these u's, we can use that natty formula up there because for each one of these, theta over n is small. So this can be written as 1 minus I theta over n tau plus stuff which we're going to be able to neglect. This is raised to the nth power because there are n of these terms on a psi. And now we take the limit as n goes to infinity to be completely sure that this plus dot 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 stuff can be neglected, right? This plus dot 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 stuff is order theta over n squared. So to be sure it can be neglected, we can go to the limit n to infinity. And then we have a theorem of calculus that for what this 1 plus a bit plus something over n raised to the nth power goes to an exponential. So this mathematics now tells us that this is the exponential of minus I theta tau operating on a psi. So we introduced tau as the first order Taylor series term, but this apparatus tells us that that's all we need to know in order to find out what u of theta is for any theta. Which is, I think, slightly surprising. You don't need to know anything in the higher orders. What do we say? We say that tau is the generator of both the unitary transformations, unitary operator rather, and the transformations psi goes to psi primed. We say it's the generator. By saying it's the generator, this is badly written, tau. But The generator is the operator you stuff in up here in the exponential. It's always times minus I for conventional reasons, and then a parameter theta that tells you how much you've generated. So, for example, P over H bar, not P sadly, but P over H bar is the generator of translations. That's just jargon. So now let's think about, time to move to a new board, think about rotations. This is where it becomes slightly more interesting because we will discover that in quantum mechanics, rotations seem, well, they're rather more complicated. They seem a bit different from, they are actually significantly different, or quite amazingly different from rotations in classical physics, and I think this is not fully understood even now. All right, so to generate translations, we in fact need three operators, don't we? We need px, py, and pz. Why do we need three operators? Because to define a translation, we need to specify a vector, because we have to say in what direction we're going to go and how far we're planning to go. And those three numbers define a vector. Or alternatively, we can say, well, okay, you know that. So we should expect that there's more than one generator of rotations, because in order to specify a rotation, we have to specify a rotation axis and how far around that axis we're going to go. Right? If you know the axis around which, so here's a solid body, I can rotate this in a whole variety of ways. To specify one rotation, I specify the axis I'm going to rotate around, and I specify how far around that axis I'm going to rotate. So we expect three generators of rotation because we specify a rotation with three numbers. Now, there are many ways, just as there are many sets of three numbers I can use to specify a translation, because I can orient my x, y, and z axes in any which way I like. There are many ways in which I can specify three numbers that define a rotation, and those of you who've done S7, the classical mechanics option, will have heard of Euler angles, of which there are three, theta, phi, and psi. But the handiest way to specify three rotations is actually through a vector. We're going to use alpha. So that's alpha x, comma, alpha y, comma, alpha z. So an alpha hat, the unit vector, so this now doesn't mean an operator, it means a unit vector. Unit vector parallel to alpha is axis of rotation. And mod alpha, ouch, the modulus of the vector alpha is the angle through which we plan to rotate by. Okay? So these three numbers are a handy, convenient system for specifying which rotation you wish to refer to. And I now say that there must be, so the rotations form a continuous set of transformations of my system, because I can rotate my system by a little bit or a lot. And so there must be a state of the system which differs from my previous state only in being rotated. And this state must be reachable by some unitary operator, u of alpha. And this apparatus here tells me that u of alpha can be written as an exponential of minus I alpha dot j, where this is playing the role of tau, this is the operator, It's a set of three operators as promised, because this means alpha x jx plus alpha y jy plus alpha z jz. So it's a set of three operators, jx, jy, jz. They must exist because, and it's going to be Hermitian. It's going to be Hermitian because this operator is going to be unitary. And we've shown the connection between Hermitian operators and unitary operators. So I hope that much is absolutely self-evident, or will be when you think about this through again. There must be this operator. It's going to be Hermitian, so it's going to be a candidate for an observable. And the question arises, what observable is it going to be the operator of? The operator associated with translations, which had to exist, it was a logical necessity that it existed, and we have shown that the operator is actually the momentum operator divided by h bar. So I hope it won't come now as a great surprise that this operator is going to be the angular momentum operator. We're not proving this. I'm saying it will turn out to be angular. Oh, sorry, that's terrible. Angular. So the angular momentum operators are the generators of rotations in the same way that the momentum operators are the generators of translations, but we will we will have to build confidence that that's the case as we go along. I'm saying that this will turn out to be the case. I hope it will be clear. At the moment, I just hope that that's a plausible conjecture that it is the angular momentum, that we're talking here about the angular momentum operators. And of course, the reason there are three of them is that angular momentum itself is a vector, so you can have an angular momentum around the x-axis, an angular momentum around the y-axis, and an angular momentum about the z-axis, and that's because you have those three numbers, you have three operators. And we're going to have the analog of, well, this formula here is going to be that d by the alpha, the modulus of this angle, d by the alpha of psi primed I times this is going to be the unit vector alpha dot j on psi. You might want to just check the algebra on this. If you do the derivative, so why is this a function of alpha? Only because this is u, which depends on alpha, on psi, which does not. So we're talking about the derivative of this exponential with respect to the modulus of the vector, but this exponential could clearly be written as mod alpha times the unit vector alpha. Do the derivative and you'll find this important relationship here. So what does the operator alpha, this is just a single operator. If you take the unit vector alpha and you dot it into the three operators j, you get a linear combination of these three operators, which is an operator. And what does this thing do for you? It measures the rate of change of your state when you rotate it around that axis that's specified by this. That's what it's physically doing for you. And this is an important relation we'll come back to. Okay. We're not going to quite finish this, but let's get going. So we've talked about translations and rotations, and they have this in common that they have a free parameter, how much you do of them, which you can turn right down to zero when you do nothing, and they just become the operators just become the identity. But we have to use in physics, we have important use to make of transformations which are discrete. You cannot turn them down to nothing. You either do it or you don't do it. And the classic example is the parity or reflection operator. So if I have an ordinary vector, then P turns the position vector x into minus x. There is a transformation you can make where you start with a thing and you choose a point, which you call the origin, and you move every part of your thing through that origin into another thing. So if the origin is here and my lower hand is here, if I move every part of my lower hand through the origin by a certain amount to this equal distance opposite from the origin, it should become my upper hand, my right hand. Right? Left hands and right hands are related in this way through reflection through the origin if you put the origin symmetrically between the two. So this is a transformation you can make. This is a mental transformation. It's not a real physical transformation, but it's a mental transformation. You could ask yourself, suppose I had a system which was obtained from my real system right here in the lab by this operation. A question you can ask is, would the dynamics of this system, so as my real system around here is moving around, imagine this thing is a solar system or my hand wiggling, would the system that you get above by mirroring each of these points through the origin, would that behave like a real thing in the universe? And in classical physics, that's the case. What you see down here, reflected through the origin produces a wiggle up here, which could happen all on its own. There would be a dynamical system that would produce that wiggling. One of the great discoveries of the 20th century was that that's actually not true in all physics. When weak interactions are involved, things happen. If you make a model by taking your real system and playing this silly game with it, you get a thing up here which you can distinguish from a real system because the real system up here couldn't behave in that way. So there is this operation of taking your system and mirroring it through the origin, and there's a classical operator P which does this. It just changes the sign of all vectors, right? Of all components of a vector. It turns x into minus x. It puts a point to the opposite point across there. So what's the quantum mechanical analog of this? Well, it's this animal. So I'm going to have a long tail on P to imply a classical operator, which simply changes the sign, right? This is classical, and it's just a change of sign of all vectors. Okay. We want a quantum analog, and the quantum analog is the thing this. I'm going to define it thus. What's this? This is the amplitude to be at x if you're in the state of psi primed. I should have written this separately. This is the amplitude so P at psi is going to make a new state. What state is it going to make? This state. What's the point about this state? The point about this state is if you're in this state, the amplitude to be at x is the amplitude to be at minus x if you're in the original state. Right? So this is our original state, and the amplitude to be at minus x in this state is equal to the amplitude to be plus x in this state, which we've gotten by using P on psi. So P takes the state of my hand here and makes this state. That's what it does. And what can we say about, what interesting statements can we make about this? Well, one very obvious statement that we can make is that if we look at x p squared at psi, then that's x p at psi by definition, obviously. We use this rule here on this state, so that's equal to minus x on p at psi, right? Because this p and that x, using that rule on this state, gives me this. I'm replacing psi in this formula by p at psi. And now I can play the game all over again. So by using the same rule, I find that this is equal to minus x on psi, which of course is equal to x on psi. So if you use, what does this tell me? It tells me the amplitude to be at x when I'm in the state p squared at psi is the same as the amplitude to be at x if I was in at psi. In other words, these two states are the same. So that implies that p squared is the identity operator, which implies that p inverse is equal to p. P is its own inverse. And what I should do next is show that P is Hermitian, but we'll have to do that tomorrow. And therefore, P is going to have the properties of an observable.